In this video, we're going to look at probably the most famous example of the wave interference, and we're going to look at it in the context of light interfering. If you know anything about light, and you may not know this, but the one thing that light is a combination of electric and magnetic fields. So light can interfere with itself because it is a wave. It has wave-like properties. And what's really happening is it's actually the electric field inside that creates this light that's going to interfere. When we look at what we call the two-slit experiment, or the Young's double slit experiment, what we do is we start off with a light source, and we send it through a sheet, and we have it create a single point. So it comes off of this boundary here, comes off of this little piece of cardboard and emanates out as a single source. Well, then we put three more pieces of cardboard in there with two slits, forming two slits. So when the light hits one slit, it looks like there's a source of light here. When light hits this part of the slit, it looks like there's another source right there. And both of them emanate from those 2 points, and they start to go out in a spherical pattern. And because they were created from the same source originally, they're going to be in the same wavelength, and they're going to have the same phase, which means they're going to be coherent. If they're coherent, they can interfere. So we create the light, we send it through two spaces, create two identical sources, and then we're going to see what happens on the screen in the background. And really, this is nothing more than what we've talked about in the past of interference. The two waves are going to interfere. They're going to be light waves that are going to interfere, but they're going to interfere exactly the same way as before. We're going to look at their optical path length and see if they vary by a full wavelength, by a half wavelength, by somewhere in the middle. And because of this, we're going to get an interference pattern that's going to show up on the wall. So let's actually see. So if we wanted to see what a moving version is, we start off with our light source, goes through two light sources, and we're going to get this interference pattern. So the antinodal lines are going to be here, here, and here. The nodes are going to be where the dark spots are, these dark bands. So we see a band of dark spots, and it'll create a dark spot on a screen at the back. So if we were to plot what happens, we're going to get a bright spot because of the antinode. We're going to get a dark spot because of the node. We're going to get a central bright spot, followed by a first dark spot, our first minimum, and then our first non-center maximum. So if we wanted to start labeling these, we could take a guess that this is going to be m equals 0, this is m equal 1, negative 1, this would be m equal 1/2, and m equal negative 1/2. But before we get too ahead of ourselves, we can actually look and see what happens. So this concept, we already have all the physics that goes through this. And the physics is, if we have two waves with the same wavelength, with the same phase, they can't interfere if their path lengths are different. So if we know their path length, and we know the difference of their path length, we can figure out if it's going to be maximum, a minimum, or something in the middle. So the problem we're left with now is just actually geometry. We're just going to look at this setup. We have two spots that are going to produce light, and they're going to be some distance d apart. And we're going to label the distances, or the angles, to these maximums as, theta 1, theta 2. It's going to have a corresponding y1, y2. But this is really all just geometry based off of a simple triangle. So when the light comes from this point here, it has to travel all the way to the screen over here, whereas this one has to travel a little bit of a shorter distance to get to the same spot. So if the top slit goes there, there's one path length. From the bottom slit, it goes to the same spot on the screen. That's a different path length. So what we can look at is we can look at the path length. So we count, again, the number of wavelengths that it takes to get through there. So knowing the distance from here to here, we can use an approximate triangle to come through that. So we can use this angle and the hypotenuse compared to this. And we know that at the first minimum, or the first maximum, that the difference of the wavelengths is going to be exactly one wavelength. So I start at the top, go 1, 2, 3, 4 to a minimum, so 4.5 wavelengths. Here I start at the top, go 1, 2, 3, 4, 5.5 wavelengths, so path difference of one wavelength. So we construct a high point at this point up here. At another point up on the top, there, the distance from here to there and the distance from the top slit to the screen, bottom slit to the screen, top slit to the screen, for m equal 2 is going to be 2 wavelengths. And we can work out the geometry. And what we'll find that if we were to do this, we approximate this little triangle in here, and the distance between the two slits is the d. This is our hypotenuse. There's a right triangle right here, a right angle. So that means this length right here is d sine theta. But we know that d sine theta has to be exactly equal to one wavelength to get a maximum. So we say that d sine theta is our path difference. It's just the difference between this path and this path. So d sine theta is equal to m lambda. So if m is an integer, then that's going to be a bright spot. If m is a half integer, then it's going to be a dark spot. So again, the destructive one, if that distance, the difference between the two, that d sine theta, which happens to be the same theta as this angle here, if that d sine theta is equal to a 1/2 lambda, then we get a dark spot, or 3/2 lambda, we get a dark spot. So again, the same thing we did before. This time, we're just going to put a little bit of geometry on the triangles. There is one additional problem that you can look at, and we can say how far along the screen. So not necessarily what angle it's at, but how far it is along the screen. And we can just work out a simple triangle to figure out what these distances y1, y2 is, if we know this distance from the double slit to the screen itself. So again, it all just comes down to the geometry and knowing that the interference pattern has to have a path length difference of m lambda, where m has special properties if it's for constructive, or m is a half integer value if it's destructive.